Hello and welcome. My name is Mehta Akshat Kumar and my student ID is 1129239. And I am here to present my thesis, which is completed as a part of my Master of Science degree in Machine Learning and Artificial Intelligence at Liverpool John Moores University. In thesis, my thesis supervisor Aayushi Verma has carefully guided me on this journey, providing endless support and profound insights throughout the duration of my research. In addition, my LJMU professor Dr. Ahmed Kaky, whose extensive knowledge and innovative teaching methods have greatly enriched my learning experience and have helped shape this research. Today, I will discuss my thesis titled with Gen AI LLM Potential for Automation Test Case Generation from User Stories in Software Engineering. Today, I will share how this research can transform and enhance the software testing processing with using Gen AI techniques in quality assurance domain of software development. Thank you for joining, and I am excited to share my findings. Let's move to our next slides to agenda. In today's presentation, I will begin by exploring the motivation behind my research and introduce the key concepts. I will discuss the importance of user stories in software testing and the research gaps my thesis addresses. I will identify the problems in current practices, followed by the research questions, aims, and objectives that guided my studies. I will then look at the research methodology and visualization, the 30 experiments conducted, along with the evaluation metrics used. Then I will walk you through the end-to-end experimentation of these all 30 experiments, followed by an analysis of input data sizes and the result from zero shot, few shot, and chain of thought prompting techniques. I will review the key insights and the final findings from the experiments, dwell into advanced techniques like three of thoughts frameworks, and demonstrate how these concepts have been implemented in the story to test GPT application. Finally, I will conclude with the discussion of the contribution to the knowledge and future recommendations. Let's move to the slide 3, where we will dive into the motivation behind these studies. In 2022, when I started my working as a software engineer in my current organization, iNexure Solution Limited, as a front-end and QA engineer. My job was to make sure that software was free of bugs as possible. This meant I had to do a lot of manual testing, writing detailed test cases for each feature. Writing these test cases was just not about the writing down steps. It was thinking about of every possible thing that could happen where someone used the software. You can take example like it was like trying to predict every move in a chess game, tedious and time consuming. After doing this for 2 years, I started to see just how repetitive and exhausting this was. Every day I spent lot of hours writing these test cases, no matter how have I tired. I knew that being a human meant I miss might be something. It was just a tiring. It also took up so much time. All that time spent writing could have been used for more important tasks like actually testing the software. When I was working, I was studying in this AIML program from Liverpool John Moores University. As a QA engineer facing this problem for the test case generation in a QA process, and as an AI student, I thought that I could find a solution. That got me thinking that had a better way. What if I found to give this tedious, repetitive work to something that doesn't get tired and miss details? That's when I start thinking about the potential of artificial intelligence, specifically LLM models, can handle a lot of information and generate content based on what it has learned. So I thought that why not use the AI automatically generate test cases? The idea really excited me for this thesis idea. So let's move to the next slides. First, Choosing the right path for gathering requirements. Clear and precise requirements are essential for the software development. There are many ways to gather requirements, such as interviews, documentation, and use cases, but we choose the user stories. User stories often a clear, flexible narrative format that evolves with projects and captures the essence of what users truly need. We will explore more about it in the next slide. Second, crafting detailed test cases using the SDLC and ISKTP standard. As a QA engineer, I often saw how rushing to meet deadlines led to incomplete test cases, which resulted in the rework and cost overreturns. To improve quality, we need detailed test cases that follows the SDLC principles and ISKTB standards, including the key elements like the test case ID, test case description, test case priority, and severity. This ensures that early bug detections and reliable softwares. Third, exploring generative AI for the test case generation. I explored the different technologies like traditional ML, NLP approaches, and the generative AI approaches. In that, generative AI stood out of its ability to automate complex tasks by learning from the large data sets. Also, unlike previous research that focused on individual methods only, I identify a gap in the comparative analysis across these techniques, which I address in my thesis. By combining well-defined standards, user stories, and the generative AI techniques, we can save time, reduce manual efforts, and focus more on the quality testing as demonstrated practically throughout the story to test GPT application. Next. In next slide, we will descriptive that there are many ways to gather client requirements, like writing the detailed specification, creating use cases, or conducting interviews. But here, why user stories are often the best approach. Let's understand with example. Here you can see the example that as a register user, I want to able to reset my forgot password so that I can regain access to my account without having to contact customer support. Here in user story, it's a specific format like as a I want so that. So let's start with the first point. User centric design. User stories focus on the user's needs. Like you can see in the example here that are specifically focusing on the customer forgot password functionality. This approach ensures that the development prioritizes users' convenience. Second point, clarity. User stories are straightforward, making it too easy for the its all team members, including developers and non-technical staff, to understand that requirements and the objectives. Third one, adaptability. User stories allow to the flexibility, changes or additions such as a new security features for the password research can be integrated smoothly into the development process. The fourth one, seamless testing. Each user story can be directly converted into a test case, ensuring that features like password reset function as intended and meet user expectation. Fifth, collaborative approach. The creation of the user story involves the contribution from the various stakeholders including the developers, testers, and users, ensuring that the comprehensive coveraging for all users' needs and the scenarios. Next slide, we will be explore to the insights from the literature review, which I am listing, highlighting the research gaps. Let me walk you through the some key research gaps in the field that I have identified based on the common themes in the current studies. First, while traditional methods of requirement gathering are well explored, there is a gap in the integrating AI into this process to improving efficiency and accuracy. AI has great potential here, but has not been fully tapped yet. Next, testing is a crucial part of software development lifecycle, but there is not enough concrete evidence showing that how AI-driven testing can reduce defect in the real-world scenarios. More empirical studies are needed to understand AI's true impact on software quality. Third one, when comparing the manual and automation testing, we know that both have pros and cons. However, what's missing here is that comprehensive long-term benefit analysis to determine which approach is more suitable over time. In requirement engineering, user stories are widely used, but research has not fully explored now. AI can improve their creation and assessments. There is room for AI to enhance to how to handle the user story for the better software development. Now, in traditional test case generation, we separate discussion on traditional versus modern approaches. What's missing in research on hybrid models that can combine the strength of both for more comprehensive test coverage. Regarding the generative AI LLMs, they are gaining interest, especially in the test case generation. But we still need to address ethical concerns and potential biases in AI generated content. This need to more responsible use and analysis. In requirement engineering, there is a potential in combining LLMs with traditional methods to improve how we gather and analysis requirements. But there is enough research showing that how to do this practically, this is not demonstrated. There has been some exploration of prompting technique for generating test cases using AI. However, research often lacks focus on optimizing these techniques for specific domains, which could greatly improve for the relevance and accuracy of the test cases. In terms of comparative analysis, many AI-driven test case generation methods are already developed, but there is a lack of standardized metrics to compare their effectiveness and efficiency. This is a crucial for understanding which techniques provide for the best results. Lastly, when it comes to generating test cases, many studies emphasize creating code from test cases. However, they often overlook the importance of first defining detailed ISQTB aligned test cases before writing the code. This step is essential for ensuring quality and alignment with the overall test plan. This gap presents clear opportunity for the further research and innovation in AI-driven test case generation for the software development. In next slide, I enlisted some problems from this literature. We will explore this. As we move forward, I am identifying from the research gaps from the literature review in next last slide. Let's pinpoint the specific problems that these gaps creating in our field. Agile development challenges. First, speed and flexibility in agile methods often compromise detailed test case preparations, leading to quality issues. Second, manual test case creation issues. Manual test case creation remains always to be slow, time consuming, and error prone, causes the inefficiency. Third one, lack of early development focus. Insufficient attention to early project stages often leads to incomplete requirements and inadequate testing. Fourth one, LLM-based test case generation limitations. LLMs faces challenges like overfitting and limited adaptability in diverse development environments. Fifth one, inadequate evaluation metrics. Current metrics do not fully capture the quality and relevance of AI-generated test cases, affecting their practical adaptation. Sixth one, lack of QA focused research. Limited research or quality assurance in AI driven environment restricts the understanding of AI implications in the QA processes. By addressing this problem, we can enhance the efficiency and readability of the software development practices, particularly in the testing and QA processing. In the next slide, we will be explore the research question. Building on the problems we have identified, here are the critical questions that my research aim to the answer. First one, model performance evaluations related. How do various large language models perform in generating test case from the user story in the requirement engineering, particularly when different prompting technique are employed? These questions aim to identify which models deliver the most accurate and relevant test cases. Second one, what are the key factors that influence that accuracy and the relevance of the test case generated by other LLMs? How do these factors vary across the different models and prompting techniques? This question, understanding these factors, will help refine the use of LLMs in the test case generation. Third one, can we integrated the advanced framework like the tree of thoughts and explainable AI techniques like Lime and Sharp enhance the interpretability of the reliability of the model test case generated by the best performing model? These questions explore the whether these sophisticated AI tools can not only generate the test cases but also explain their logic and effectiveness, thereby increasing the trust and usability in the real world applications. This question guides the direction of my thesis, aiming to push the boundaries of how AI can be leveraged to improve the process of requirement engineering and quality assurance in the software development. In the next slides, we will be exploring the aim and objectives. Let me go you through the core aim and objective of my research. My end goal of my thesis to examine how we can use generative AI, specifically LLMs like GPT-4, Gemini 1.5, Llama 3, Llama 3.1 to automatically test cases for user stories. We aim to develop methods that are accurate, detailed, and fit to the software development specifically for the QA research. For that, I created some objectives. First one, experimentation part. We will test different AI models from the prompt methods to generate test cases covering all potential techniques. Second one, analysis. We will evaluate the test cases using the metrics such as rough, BERT score, test coverage, readability, context matching, etc. to measure that quality and effectiveness. Third one, integration. We have to plan to best models by adding frameworks like TOT and explainable AI techniques. This will make the test cases both reliable and easy to understand and along with the trustworthiness. Fourth one, development. All along with the found the research, we will create the app called Story to Test GPT, incorporating our findings. This tool help to quality assurance professional to generate and review the test cases effectively. Yeah. So next slide, we will focus on our research methodology of our thesis. Let's walk through to end-to-end workflow of this thesis, which is crucial for understanding how we approach the automatic task generation using AI-driven techniques. I will be break down into 6 steps. First one, data preparation. In this step, we gather the crucial data like project details, feature details, and user story title with the 5 accepted criteria. Then we can clean and standardize it to ensure that it's reliable and uniform, setting the stage for accurate task case generation. Second one, prompt creation. We will design tailored prompt using techniques like zero shot, few shot, chain of thought, which help to direct the AI models to generating precise and relevant test cases. Third one, experiment execution. Each prompt is tested across various LLMs under the uniform condition to fairly evaluate the performance in the generating test cases. Fourth one, performing evaluations and key insights. We assess the model's outputs using the metrics such as the rough score, BERT score, BLU score, readability, context matching, final OPI, analyzing their accuracy and completeness to determine the most effective model and the prompting technique. Fifth one, integration of advanced techniques. In this section, the top performing models are enhanced with the tree of thought framework and explainable AI methods like LIME and SHARP, which aid to understanding the reasoning behind the AI decision and ensure robust test case generation. Sixth one, application in the development. We translate our research into practical implementation like a story to test GPT designed for the QA professional. This tool incorporate our best techniques into a streamlined user-friendly interpret powered by the Streamlit, making it to tangible probable for the industry use. This end-to-end workflow not only demonstrates the throughout of my research but also highlights the practical steps I have taken to ensure that my findings can be applied effectively in the software development industry. I will go through the visualization of 30 experiments, like how can I conducted my 30 experiments. In this slide, I am presenting how I structured and conducted 30 experiments as of part of my thesis. This experiment were designed using 3 different prompting techniques as you can see in this slide. There are 3 prompting techniques, zero shot, few shot, and chain of thought, applying across the 10 different LLM models combinations. These combinations result into total 30 unique experimentations, like 3 prompting techniques and 10 LLM models equal to 30 experiments. This visualization here illustrates the experimental setup showing how each prompting technique was symmetrically applied to each model. Let's next to slide in which we can evaluate the evaluation matrix. I will explain the 6 key evaluation metrics I used to assess the quality of test case generation in my thesis. First one, rough score. Rough score can help to how much overlap there between the reference test cases which is given in the input data and the generated test cases. Specifically, they evaluate the content accuracy by the comparing the similarity in words level, first level, and the sequence level. Second, BERT score. BERT score go a step further by assessing the semantic similarity between the generated and the reference test cases. This means by their check if the meaning of the test cases is preserved, not just by words. Third one, blue score. The blue score evaluates the precision of the generated test cases by comparing the words and phrases used in them with the reference test cases. It's about how well the generated test cases match the expected ones in the terms of wording. Fourth one, readability score. This metric determines how easy to read and understand the generated test cases. A higher the readability score means the test cases are clear and easy to follow, which is important for ensuring that they are useful in the real world testing. Fifth one, test coverage. Test coverage checks all the expected criteria from the user story are addressed by the generated test cases. This matrix ensures that not important aspects from the user story are also missed in the test cases. Sixth one, overall performance index. Finally, the overall performance index or the OPI combines all these above individual matrix scores into a single value. This index helps to assess the overall effectiveness of each experiment with the combination of each model and each prompting technique in generating high quality test cases. This matrix together provides a comprehensive evaluation of how well the generated test cases meet the standards of accuracy, clarity, and completeness of required the effective software testing. After seeing the evaluation matrix, let's move to the next slides in which we can see that end-to-end experimentation of the implementation. In this slide, I will walk you through the step-by-step process of how each of the 30 experiments was conducted in my thesis. First, data collection. We started by gathering all the necessary data, which included the project details, feature details, user stories, and the accepted criteria, and the reference test cases. This data formed the foundation for the generating new test cases. Second step, data preprocessing. In that step, the data was cleaned and organized. This step ensures that the user story and the other outputs were in the correct format for the AI models to the process effectively. Third one, create basic prompt. A basic prompt was the created to instruct the AI models that how to generate the test cases. This prompt provided the initial guidance needed for the models to understand the task. Fourth, selection of the LLM model. In this section, one of the 10 LLMs for the experiments we can choose. Each model has its unique strength, and this step allowed us to test that which model perform best under different conditions. Fifth one, apply prompt techniques. The chosen prompt techniques from the zero shot, few shot, or chain of thought was applied to the model. This technique influenced how the model generated the test cases, offering different level of guidance. Step 6, execution of the experiment. The experimentation was then executed when the LLM generated test cases has based on the give the user stories and the prompts. This is the core of the process where the AI produces the output. Step 7, organization of the generated test cases. After generation of the test cases were organized symmetrically, this step ensures that the output was easy to analyze and the compare across the different models and techniques. Step 8, evaluation of the generated test cases. The generated test cases were then evaluated using the matrix I explained earlier slide, such as rough, broad, blue, readability scores, etc. This evaluation assessed the quality and effectiveness of the test cases. Step 9, calculation of the final OPI of the experiment. We can calculate the final OPI of each experiment, the OPI combined of each individual matrix into a single score, allowing to compare the performance of different models and techniques. Step 10, analysis and documentation of the results. For each experiment, I generated the visual graph for all individual matrices which are linked in the appendix CD of my thesis. Additionally, all the generated test cases were stored in the PDF format and also included in the appendix. This detailed documentation provides a comprehensive of the results and supports the overall analysis. Let's move to the next slides where we analysis of different number of input data sizes with the final OPI. In this part of my research, I had to make a critical and crucial decision due to the financial and technical constraints. Initially, I planned to use 500 samples to throughout the test the model, but the cost associated with the using the paid models like the GPT-4, Gemini 1.5 Pro, and Flash, along with the significant time and the resources needed to this process such a large data set, exceed or the budget and the timeline. To ensure that the study could be completed on the time and within a budget, I decided to reduce the dataset size of to 100 samples only. Now, you might wonder that if the reduction compromise the quality or the readability of the findings. The good news is that it didn't. My experiment shows that the reducing the dataset did not negatively impact the results. The overall performance index scores remained consistent across both 100 and 500 data samples for the all the models. Like I tested some models you can see in this graph. For instance, the model of Llama 370 billion achieved an OPI 0.7213 with 100 samples and the 0.7229 with 500 samples, showing only a minimal difference. Similarly, model like a Llama 3.18 billion instance and Gamma 7b displayed the nearly identical OPI scores regardless of the data set. This consistency across the different data sets confirms that the using a different smaller data set still providing reliable and meaningful results. This decision to reduce the data size accurately had some advantages. It's allowed for more efficient analysis while still maintaining the integrity of the study. It also demonstrated that even with a fewer sample, the models could generate accurate and comprehensible test cases, making the findings robust and trustworthy. In summary, by reducing the test data sizes, I was able to complete my research within a constraint which while ensuring that the results remain thus valid and insightful. Let's start the analysis of different prompting techniques in the next slides. Let's start with the key insights from the zero shot prompting technique. In that, you can see that Llama's 370 billion performed the best across of all rough scores with a strong rough 1 score of 0.06742, showing the good alignment and relevance to reference test cases, is also led to in rough 2 and rough L, demonstrating the fluency and structured preservation. In contrast, Gamma 7b it had lower score, struggling with the relevance and coherence. For the BERT score, GPT-4 achieved the higher precision 0.65617, closely followed by Llama 70 billion 819b, Gemini 1.5 Flash had the best recall at 0.06614, showing strong content coverage. Overall, Gemini 1.5 Flash balanced the precision and recall with the highest F1 score at 0.64092. In summary, Llama 370 billion 8192 consistently performed well, while Gamma 7b it faced the challenges in relevance and structure. Continuing with the next results, zero shot prompting technique. Let's focus on the additional metrics for like blue scores. Llama 270 billion had the highest at 0.10064, showing the best result with the reference test cases, while Gamma 70b it scored the lowest, indicating weaker word performance. In terms of readability, Gemini 1.5 Flash led with a score of 0.522803, producing clear and user-friendly test cases, while Llama 3.170 billion Versatile had the lowest readability score. For the test coverage, Llama 3's 8 billion 8192 excelled coverage more accepted criteria, while Gemini 1.5 scored the lowest. When it comes to the context matching, again Llama 370 billion once again growing among all the models, showing that strong relevance to the user stories. Where areas Gamma 7b it's very struggled. Overall, Llama 370 billion was the best performer across all the metrics with the final OPI of 0.0767244, while Gamma 7b had the lowest, indicating it faced the challenges with the alignment, relevancy, and fluency. Now explore the key insights from the key few shot prompting technique, focusing on how well perform models based on the rough and BERT score. In that, you can see that Llama 370 billion 8192 emerged as a top performer across the rough scores, once again same as zero shot prompting with a rough 1 score 0.0703391, reflecting strong alignment with the reference test cases. Is also led the in rough 2 score with the 0.0394549 and a rough L with a 0.497632, showing excellence, fluency, and structural coherence. On the other hand, Gamma 7b it again had the lowest rough one score and rough 2 scores you can see as that 0.55544378 and 0.288386, and the rough at like 0.03477, indicating challenges with relevance and maintaining structure. For bird score, GPT-4 had the highest precision at 0.66875, closely followed by Llama 70 billion 8192 at 0.6576883, reflecting strong word uses. Gemini 1.5 Flash led in recall with 0.61931, capturing essential content, while Llama 3.170 billion versatile had the lowest recall at 0.4545858. Overall, you can see that Llama 370 billion 8190 continuously outperform other models with strong across all metrics, while Gamma 70 billion struggled with the fluency and structural alignment, making it the weakest model in the setup. Let's continue with the next slide. Continuing with the few shot technique, Gemini 1.5 Flash achieved the highest blue score of 0.03902, showing strong and sequence alignment with the reference cases. In contrast, GPT-4 had the lowest blue score, 0.04 5631. For readability, you can see that Gamma 29B it led with the 0.481938, making it the more user friendly, while Llama 3.18 billion instead scored the lowest is 0.391822. When it comes to the test coverage, GPT-4 excelled with the 0.785894, with Gamma 7B it had the lowest 0.13354, missing the key elements. In context matching, Mistral 7B Mistral 8X7B, it's led with the 0.72931, while Gamma 7B align again lagged with the 0.57128. Overall, Llama 370 billion emerged as the top performer with the highest OPI at 0.77, excelling in the all key metrics. On the other hand, Gamma 7B recorded the lowest OPI at the 0.72856, struggling with the relevance and the coverage. Let's move forward to chain of thought prompting exploration. In this slide, I will explore the key insights from the chain of thought prompting, focusing on the performance of different models. Let's start with the rough score. Llama 370 billion 8192 excelled again with the rough one score with the 0.705317, showing strong relevance, alignment, and same as earlier, both techniques like zero shot and few shot. Gamma 7 beats the lowest 1.551145 in rough 2. Llama 70 billion 8192 again led with the 0.38926 accuracy OPI, indicating strong fluency, while Gamma 7 billion scored lower at 0.29416. Rafael showed Llama 3 ahead with 0.48776, preserving structure, where compared to Gamma 7B it at 0.5354821. For the bird score, Llama 3 8 billion 8192 led in the precision 0.4661661 OPI, while Gamma 1 Gemini 1.5 had a lower precision at a 0.611043. Bird score recall was the highest for the Gemini 1.5 Flash at 0.651954. While Llama 3 8 billion 8192 scored for the lowest is a 0.54485. Gemini 1.5 Flash also led in the bird score F1 at 0.63587, showing that the best balance between the precision and recall, while Llama 3 1.170 billion versatile was slightly lower than the 0.585042. Continuing with the next slide. Starting with the blue scores, Llama 3.1 instance led with the 0.8084845, showing the strong one and alignment with the Gamma 7B. It scored lowest is 0.019791, indicating weaker alignment. For readability, Gemini 1.5 Plus scored highest with the 0.510044, producing more readable test coverage, while Llama 3.170 billion versatile had the lowest at 0.03081776. Next, with the test coverage, Llama 3.170 billion versatile excelled with the 0.800586, covering most of the key suspect, With the Gamma 7, we had to lowest points 178,925, missing the important details. With the context matching, Mistral 8x 7 billion led with the 0.729331, showing strong alignment with the user story, while Gamma 70 billion scored lowest 0.58625. Finally, the overall performance Gamma to 9 billion, it scored the highest at 0.779801, while Llama 3.170 billion versatile scored lowest is 0.724432. In summary, average we can see that Llama 370 billion performed best across the like rough one and test coverage, while Gamma 7B struggled across the server key areas, making it less effective model. Next, we will move to the key insights from the all the 30 experiments one. As in this slide, we can look the key insights from the 30 experiments conducted using different prompting techniques and models. Several important patterns I can found from your battery insights. First, execution time versus performance. Model like GPT-4 showed the longer precision times correlated with the higher accuracy in metrics like rough and bud score. However, this require more computational resources, highlighting a crucial trade-off between the accuracy and efficiency. Second, chain of thought impacting COT prompting notably enhanced model reasoning abilities and alignment with the user story context, leading to more relevant test cases. Third one, model size and accuracy. Larger models, notably Llama 370 billion 8192, were more successful in generating accurate and contextually relevant test cases, demonstrating the importance of the model capacity for achieving high accuracy. Fourth one, test coverage. Techniques like COT and few shot prompting consistently improve the test coverage, with models like Gemini 1.5 Pro excelling ensuring comprehensive coverage of user stories. Fifth one, readability. High readability stores from models such as Llama 70 billion 819 to make them particularly valuable in the QA environment where clarity is essential for the effective testing. Sixth one, BERT score, precision and recall. Few shot and COD prompting boosted BERT score metrics across models like Mistral's 8x 7 billion, enhancing their ability to mirror the essence of the relevance test cases accurately. Let's continue with the next slide. Blue score. Higher blue score were noted with the COT prompting with Llama 70 billion excelling in the fluency and symmetrically accuracy. Next, context matching. Model like Llama 370 billion 8192 and GPT-4, especially with the prompt COT prompting, achieved the excellent context matching, ensuring the test case align well with the user story. Next, overall performance index. COT prompting techniques led the highest OPI score, making models like Llama 370 billion as a top performer due to their balanced accuracy and test coverage. Next, cost versus performance. While paid models like GPT-4 offer the higher accuracy, they also demand to more resources and time, underscoring that the cost accuracy trade-off. Next, few shot effectiveness. This prompting was particularly beneficial for mid-sized models like Llama 3 8 billion, providing a particular balance between the resource use and the accuracy. Last not but the least, consistency across the metrics. Reliable performance across multiple metrics like rough one was observed in the models employing COT prompting showcases this consistency in the test case generation. These insights reinforce the value of COT and few-shot promptings, particularly in the maximize model performance, while balancing the cost and execution time. The consistent success of models like Llama 370 billion and GPT-4 across the multiple metrics, highlighting that the reliability and the effectiveness in generating high-quality test cases. Let's towards the final findings of our test case generation. After thoroughly analyzed from last many slides, the results from the 30 experiments, it's clearly that Llama 370 billion 8192 stand out as the best LLM model for the test case generation, consistently delivering the high accuracy coverage and the context alignments. On the other hand, Gamma's 7B it was identified as the worst performing model, struggling with the relevance and the coverage. Among the prompting techniques, chain of thought prompting proved as the most effective, enhancing the model reasoning abilities and resulting in the highest OPI scores. Conversely, zero-shot prompting techniques was the least effective, often leading to lower accuracy and the coverage in the detailed test cases. This finding highlights the importance of the selecting both the right LLM model and the appropriate prompting techniques to optimize the test case generation task in the Gen AI field. Let's move on to the implementing of the tree of thoughts framework. In this slide, I will explain that how tree of thought frameworks were integrated into my thesis to enhance the process of generating high quality test cases from the user store. First one, processing the input data. The process begins with the loading and extracting the essential information from the input data, which includes the user story related and the project related and the feature related details. This step ensures that the data is properly formatted and ready for the subsequent steps, same like the earlier 30 experiments. Second one, integration of the tree of thought prompting frameworks. Once the data is processed, the TOT framework is integrated. The framework plays an important is crucial role in the structuring of the reasoning process, helping the model to generate more logical and coherent path for the test case creation. Third one, formulating and sending the prompt. The next step involves the creating and the sending a prompt to the model. This prompt request to the model to generate the various reasoning path behind the based on the provided input data. These paths are essentially different approaches or you can say as a thoughts that the model consider when the generating the test cases. Fourth, receiving and parsing the through the thought path. After the model generate the reasoning path, they are received and broken down into like understable components. This step is important because it allows us clearly see the evaluated path proposed to the path. Fifth one, evaluating thought path. Each generated thought path is then thoroughly evaluated against the several criteria, including the alignment with the project goals, feasibility, completeness, consistency, edge case handling, and the clarity. This evaluation ensures that only the most effective and relevant thought paths are considered for the generating further all the final test cases. Number six, selection of the optimal thought path. Based on the evaluation, the thought path are scored and the high scoring path are selected as the optimal one. This selection process is crucial for the ensuring that the final test cases are generated from the best possible reasoning, providing a strong fit for the project needs. Number seven, generating the test cases. Finally, using the best case path, the detailed test cases are generated and the evaluated using the various metrics to ensure that they are meet the desired quality standards as per the accuracy, coverage, and the readability. So these all are the six steps integrating into tree of thought frameworks into my thesis. I was able to enhance the reasoning process behind the test case generation, leading the more effective and well-structured test cases that are better aligned with the project's requirements. Next, move us to the key insights of the tree of thoughts. Let's dwell into the key insights gained for the implementing the tree of thoughts framework, particularly when applied to our best LLM model, which is founded by the 30 experiment Llama 370 billion 8192 with the best prompting technique chain of thought. In that, the tree of thought framework are applied and it shows that the showing results it's generating the test cases using Llama 370 8192 model, right? In achieved like high rough scores indicating good word usage and structure preservation. The bird score was well balanced, showing both relevance and comprehensive completeness in the generated test cases. While the blue and readability scores were moderate, there was still room to improvement for making test cases more clear and easier to understand. The framework excelled in the context matching, aligned well with the user story, but the test coverage was lower, indicating its need to be better coverage for all accepted criteria. Overall, TOT framework significantly enhanced the quality and alignment of the test cases with an OPI 0.7684. Throughout, there is a potential of reflecting the fluency and the coverage further. Walked through the research, analysis, and finding of my thesis. It's time to show these concepts into action, and I am excited to present a practical implementation of the story to test GPT application that I have developed, which I am integrating to in advanced techniques we have discussed, including the tree of thought frameworks and explainable AI methods like Lime and SHA. These web applications bring my thesis research to life by automating the task case generations from the user story. It's not only generating the quality test cases, but also provides explanations for that why these test cases are created, ensuring the transparency and understanding in the AI's decision making process. I will walk you through the uh, demo. Now, for inputting the data, I will fill from this any kind of dummy data. Let's take a healthcare appointment scheduling system example. I added a project description and project name, which gives the project basic details. Now focus on the feature. I will adding the feature name and the feature description, which specifically gives the details of that feature of that whole project. Now that specific feature, I will be added a specific user story title, which must follow like as a I want and so that user format. If I not able to add any this kind of words, which is standard format of this one, this give me that validation error. So it must give that specific format. Next, I will be adding related 5 accepted criterias. Now, when all other details are added, all other validations will be disappeared and it's generate the test cases with the loader in between the generation of the content. See, this is the test case generated by the story to test GPT. It gives the all the details of the input details, which is we will give the basic input details. This will generate the test cases of each accepted criteria. It will all generated each input details like test case number, title, ID, description, test case priority, preconditions, testing data, steps, post conditions, expected results, severity, type of testing, test case behavior, and the explanation of this generation behind these test cases. Why these specific test cases are covered and generated by this. This one given by the line and the sharp of the explainable AI techniques. So you can see that these are the total 5 test cases are generated. And if any user want to download that test cases, that click on that download button and it is the generated the test cases in the PDF form. You can see that the story to test GPT generated test cases. All the test case content are printed in the PDF form and anyone can share with any user or relevant QA engineer. So this is the one-to-one practical demonstrated covered by me for this my thesis idea. Yeah. So let's back to the PPT. As we move to the conclusion of my thesis, let reflects on the key contribution and the impact of this thesis on the field of AI-driven software testing. This thesis successfully demonstrates how the generative AI can be leveraged to automate the creation of test cases directly from the user story, streamlining the testing process and the reducing the manual effort. Next, the integration of the TOT framework and explainable AI techniques like Lime and Sharp significantly improve the accuracy and transparency of the generated test cases. This ensures that the AI's reasoning is clear and the results are trustworthy. Next, the practical outcome of this research is to the story to test GPT web application, which efficiently automates the test case generation. This is a tool is a direct application for the research findings, making AI driven and the test case generation accessible and the practical over the QA world. This research also highlights the critical role of early stage test case generation in agile methodologies, ensuring that the time testing is integrated early in the development process to catch issues sooner and improve the software quality. By evaluating various LLMs and the prompting techniques, this thesis provides valuable insights into which the combinations are most effective in AI reasoning and for generating the high quality test cases contribution to the broader understanding of AI's role in software testing. Overall, this thesis makes a significant contribution to the field of AI driven software testing, offering new methods and the tools that can shape the future of automation test case generation, making it more efficient, accurate, and transparent. Let's looking ahead, there are several key areas of offering exciting opportunities for the further research and recommendations. Fine-tuning large language models for the specific domains can improve the relevance and precision of the text cases. Exploring new techniques of Gen AI like RAG may boost accuracy, while integrating additional explainable AI techniques will enhance the interpretability of AI-generated results. Real-world techniques and users' feedback will ensure that the story-to-test GPT application is effective in practice, like integrating the user feedback feature. Additionally, integrating the test cases with tools like Selenium and Cypress for automation test case generation could streamline the testing process. Finally, expanding this research to the other phases of software development lifecycle, such as the design and implementation, could provide a uh, broader results. As we conclude this presentation, I want to express my sincere gratitude. I hope this journey through AI driven task case generation has provided valuable insights into the potential of Gen AI into the software testing. I extend my heartfelt thanks to my professor Dr. Ahmed Kaki for his invaluable guidance and my thesis supervisor Aayushi Verma for her unwavering supports and insights throughout this process. Lastly, I appreciate everyone who has taken to give a chance for see this presentation. Your interest and attention mean a great deal to me. Thanks.